good. So we were here. So we presented last time. We presented we introduced the idea of probability density function, the histogram, the cumulative density function, and so on. So let's see those in practice. So let's say that we have this image, and we have here. So for instance, we can see a few of the ideas that we covered the last lecture. So we have, for instance, we have a color image like this, and we can calculate the value. So the value is simply 1/3, 1/3, 1/3 of the 3 channels. Let's see how it looks like. So this is how it looks like. And we can compute the luminance. The luminance has different weights, and we now understand a bit more why we give more weight to the green channel. Yeah, so which one looks better? So both are translations, translating a color image into an intensity image. Which one looks better? Brighter, probably this one. But I would say that I can see more contrast in this one. So the difference between these small microtubules, this active filament, I think they are more visible here than here. So the information is the same, but it is simply how we are displaying this information. Okay, so and you can give any arbitrary weighting, so you can have 1, 1, 1 or whatever. So for instance, a lot to the red. So let's see how it would look like. So it is simply just the red channel. Yeah, so you can play with these weights. Okay, so then what else can we do? So for instance, here let's take the image list. Okay, so then we can compute histograms. Okay, so we can compute histogram of this color image, and then we have 3 histograms, one for each one of the channels. And this is not so convenient. So now we see a bit better. So we see the red channel here. So you see that it has a lot of black values. This is general for the black. For the red and blue area, and the reason is that there is a lot of black area here. So it should also be for the green, because here in the black there is no pixel. So that is you need the 0 in the 3 channels. Yeah, so this is how it looks like. Okay, then what else can we do? For instance, you can convert the image into a value. So for instance, you can compute the value and then compute the histogram of the value. And you know that the histogram, let's look at the color images again. So you see that this is a kind of mixture of the two. So you see this band here in the green channel, and then you see the same band in the value histogram. Okay. But you know that the value histogram is not the average of the 3 channels histograms. Okay, so we saw this in one of the previous lectures, that the average of the histogram of the average is not the average of histograms. Okay, what else? Okay, so let's see. We can compute PDFs and CDFs. So histograms is simply summing. So it is how many times we have seen a particular color, and probability density functions, they have been normalized so that the integral is 1. Okay, so we divide by the size of the image, and now the values don't go any longer from 0 to I don't know how many thousands, but they go from 0 to 0.4, 0.1, such that the area of all this curve, the area under the curve is 1. Actually, this CDF is those integrals, and those integrals you see that they add up to 1, and then they follow just the integral that you have there. Okay, so you have, for instance, here a big blue peak. So a big blue peak means that you start in the CDF at 0. You start at a value that is significantly away from 0. So for instance, this is about 45%. So that means that 45% of the blue pixels are 0. Okay? And then 100% of the blue pixels are below this 255. But it is as it should be. If you have any questions, just ask. Okay, then what else do we have? So we can show intensity layers. So for instance, let's say that I want to show for the red channel, which are the pixels that have a value, I don't know, 101 or 100, whatever it is. So all these pixels in the red channel, they have this value. What are the values? 0. So the red channel, all these pixels are at 0, exactly 0. So all these are 0. This is also black or dark, but it is not strictly 0, you see. Or it is something like 1, yeah, something. I got it this time. Yeah, this one, I don't know which value that is. ¿No tenemos un chiste, Ana? Te la sé yo.
¿Lo puedes en español?
Sí.
Sergio, voy a comprar, ¿traigas algo? Sí, compra queso. ¿Qué queso? El inventario de WhatsApp.
Okay, so and we can do the same for the other channels, so we can see where the different values are in this image. And what you see is that typically, and this is something general in images, so unless you have relatively flat areas like this one, otherwise all the values are scattered. So for instance, let's say this is 105, I don't know. 105, you have very few pixels that have value exactly 105 and 106 and so on. So if you move it to any other value, you see that the values are all scattered and they are kind of isolated points. And for a few of them, they follow, for instance, yeah, the green is not a good example, the blue. Only for those regions that are very flat, you have kind of these constant areas. Cuéntanos un chiste, Ana.
Sí.
Cuéntanos un chiste. Que nos cuente un chiste, te la sé yo.
Yo no sé contar chistes.
¿No sabes contar chistes?
No.
No se llega tarde, que llega tarde cuenta un chiste. Okay, so yeah, so this is something that is relatively unusual, and very often we haven't seen this. But when you compress images, you have this kind of effects where nearby regions they have similar values, but otherwise the more natural appearance is like this one, isolated pixels. Okay, good. Then what else? We have PDF selector. So PDF selector is kind of the same thing, but now we want to have. I think this doesn't work. Yeah. So those pixels that have a value that is above 30 and below 90. So you can select regions, and now they are more contiguous. So if you choose exactly 30, they are isolated pixels. But if you consider 30, 31, 32, they start to be contiguous. And the reason is that typically images are smooth. So smooth in the sense that if you have a value of 30 somewhere, then the nearby values will be close to the 30 there. Okay. So if you consider a range, then this range tends to form continuous areas or kind of compact areas. And what else? For instance, let's try to isolate this peak here. So there is a peak. These two pixels are not or these two windows, they are not in sync, so it is difficult to catch. So what is this value? This is 7. Okay, so let's try to move it to 7. And what is this value? How do I get it? Not easy. Okay, I don't know what goes. I cannot get rid of that one. It is approximately, so this peak here, this approximately this area. All this black background. So all the black background is this peak. Okay, what else? Then we may quantize the image. So quantization, we already saw this idea that you don't need 8 bits all the time to quantize your image. You can use whatever number of bits for the whole range. We will see that in more detail a little bit more analytically. But you can have an image with 8 bits, and then it looks pretty much like the original. The original has 8 bits. But then, for instance, let's try to reduce to 7. See what happens. So I cannot see much of a difference between these two images, but we are using half the values. Okay, so let's use a fourth of the values. A fourth of the values is still there. The two images look very much alike. There is a small region here where we start to see some artifacts, but otherwise they look very much alike. What about this? So you see they look very much similar. We can keep on reducing with 4 bits. 4 bits is not that bad. And we are using 16 times less numbers. About this, with 8, even with 8, we start to see some artifacts in these areas. You see, these are artifactual. But otherwise, the rest of the image looks relatively similar. Also here doesn't look so much. But we have reduced the number of numbers to represent from 2 to the 8 to 2 to the 3, which is a reduction by a factor of 30. Let's look at this one. Now we can see differences. Okay. So with 2, and let's go with 1. With 1, it should be very. Yeah. Now it is completely different. Okay. So let's see what we have been doing with the. Not this one. I want to stop sharing. Probably. Stop sharing. Then go out full screen. Go out full screen. ¿Cómo es algo de café de Okay, good. So what have we been doing with the quantization? Okay, so let's say that we have an image whose histogram is like this. Always put values. Okay? So this is put labels to your axis. So this is from 0 to 55, and this is the histogram of I. The value I, so let's say that it has some histogram like this, and then if you quantize by 1, so if your delta is 1, then you're calling all the values from 0, 1, 2, 3, 0.55. Okay, so now my delta is 2. Then the values I'm taking are, use a different color.
Carlos.
Pero
Yeah.
no estás compartiendo la pantalla.
Ah, yeah. Okay, so now my delta is 2, and then my steps are 0, 2, 4, all the way to 254. I cannot take 255. Now my delta is 3, let's say. My delta is 4, let's say. And then I go 0, 4, 8, 252, and so on. Okay, how many bits, how many numbers I have in each one of these representations? Okay, so let's see that this one. So if I'm going in steps of 1, then I'm having 2 to the 8 possible values. If I'm going in steps of 2, I'm going in 2 to the 8 divided by 2, which is 2 to the 7. If I go in steps of 4, I'm going 2 to the 8 divided 2 to the 2 to the 6. So these numbers here, are the number of bits that you need to represent those values. So the values still go from approximately 0 to 256, but they are going in steps. Okay, that is why what we were doing with this quantization. Okay, how do I quantize? Okay, so let's write the quantization operator. So let's say that you have a value x that you want to quantize by step delta. So this is a good round x divided by delta. Times delta. This is approximately a good quantizer. Okay, so you divide x by delta, then you compute the integer part of that, or you approximate to the closest integer, and then you multiply back by delta to make sure that it goes from 0 to 256. So let's see an example, for instance, for the blue one. So let's say I want to quantize the value 2. So this would be round 2 divided by 2, and then multiplied by 2. But this is 1, round of 1 is 1, and then 1 times 2 is 2. Okay, now I want to quantize value 3. So this is round 3 divided by 2 times 2. But now this is 2 again. Because round, well, we have just a value in the middle, but this value in the middle will be rounded down, for instance. And then we have 1 again, 1 times 2. Okay, so you see that this is the kind of step functions that we were seeing the other day. So now this is x, this is quantized by x, and it goes like this. Okay, and the exact, so for instance, for this one, the changes occur at delta half approximately. Okay, and these are 3 delta half. At this value, we got delta, okay, 2 delta, and so on. Always put labels on your plots, okay? Because otherwise they are pretty ambiguous. Any question? No question. Okay, good. Then let's go back to our slides. And we move on to the next topic, that is point processing. Okay, so let's see what point processing is. Okay, so we will do operations that simply depend on a single pixel. Okay, so let's go in of that. So here. Okay, so let's say that we have an image. And we want to produce an image. And to produce this pixel here, we use the equivalent pixel at the same location. Okay, so this is I prime. This is I prime at the location RC. And this is a function of the input image at the same location. Okay, so this is a point process. A point process is a transformation of the input image in which only one pixel is taking part. Okay, so what kind of transformations can we do? So these are the results, and then we will see the details how to get these results. Okay, so let's say that these two are our input images, and then we can increase the brightness, decrease the brightness, we can increase the contrast, decrease the contrast, we can increase gamma, that for the moment we don't know what that is. We can decrease gamma, we can make transformations to the histograms. So let's go for all those transformations. Okay, yeah, this is the same kind of equation that I have written. So the pixel at the output is a function of the equivalent location in the input image. And this is just a graphical representation of that. So, yeah, but these are the same ideas. Okay, what happens if we have a color image? So if we have a color image, you can apply the same function to each one of the bands, or you can apply a separate function to each band. Okay, so the band is this index P, so each band has its own transformation. So yeah, nothing really new. And then we have this idea of a lookup table, and this makes us think again of our concept of function. Okay, so what is a function? A function is a mapping between two sets of numerical values, or even they don't need to be numerical, but yeah, for us it is more convenient to think of them as numerical. So, for instance, if my input image, this is my input image, I am going to be transformed into I prime. This is the axis y, I prime. And then, for instance, I say, okay, my I prime will be twice the input image. I am omitting the coordinates to simplify the notation. Okay, so that means that 0 is mapped to 0, 1 is mapped to 2, 2 is mapped to 4, and so on. So at some point, when we are at 100, let's make it black. When we are at 128, this is mapping to 256. Okay, if this is a straight line like that. And then it would continue going upwards until we reach 255 in I. Okay, so what's that? So a function is something like an equation. So an equation is a way of describing a function, But actually, I can describe a function by simply giving you the table. So I can say, okay, I will construct a table, I prime, and then for I have all the values. And then for, I tell you for each one of the input values, what is the output value. So this goes to 0, 2, 4, 510. So this is another way of giving you a function. And actually, this one is much more free. I can give you whatever set of outputs that I want, in whichever range, even if there is not that doesn't exist in an analytical function that gives those values. I'm not restricted to that. Okay, so this thing here is called a lookup table. So it is a lookup table or loops, because all you have to do is, okay, what is your input? Your input is 2, then you have to substitute the 2 by 4. Okay, so that is why it's called a lookup table. Okay, so then a point process can be described by a lookup table. Yeah, remind that this +1s is something related to the way MATLAB is storing things in arrays, but we don't care about the ones. But the main idea here is that if you have a gray value in and you apply a function, then you will have a gray value out. And what you can have is a lookup table, such that when you evaluate that lookup table at this value, at this gray input value, you will have this gray output value. Okay, good. This is how. Okay, so these functions look like this. So, for instance, let's say that this is our transformation. This in the dashed line is identity. So identity means I prime equal I. So it is simply copying the same value from the input. And then our function is this black line. So this black line, for instance, here we see a part of it. So this part of it is simply, okay, you have value 104 at the input, then the output is 70. And if the input value is 105, again, if your input value is 105, then the output is also 70. For instance, if we have that transformation, have we lost information by applying this lookup table? This concept appeared the other day. So we don't lose information if the function is reversible. We can invert it. Okay, so can we invert it? If I tell you the output is 70, do you know which is the input? You don't know which one it is. So you have lost a bit of information. Not too much, probably, but you have lost a bit. So it is not a totally one-to-one transformation. Okay, good. Sorry. Okay, so for instance, I can construct this kind of transformations where this transformation is called a sigmoid, and this sigmoid goes from 0 to 255. So let's substitute x. Okay, so let's do it step by step. So let me here. Okay, so let's say that my function f x is parameterized by a value a, and this value and this transformation is the following. Okay, what is this function? So when I apply this function to a value I that goes from 0 to 255. Let's try to find some interesting values of this transformation. Let's make it right. Okay, so let's say x is equal to that was something here minus 127. Okay, so let's make x equal 0. So if I is equal to 0, then x minus, it is 0 minus 127. So this is a minus 127. Then we are changing, divided by 32 is 128 divided by 32 is 4. And then we have minus 4 dividing, we have to change the sign. So now we have plus 4. And we have exponential of plus 4 is a relatively large number, okay? So this is a large number, and this large number, we have exponential of a large number. This is a large number again. So we are dividing 255 by a large number. So we will get something close to 0. Do you see that? Okay, so we will start close to 0. What happens on the opposite side? Okay, so when x is large, so that is 255. So this is 128 divided by 32, this is 4. And now we have the exponential of minus 4 times 8. So this is an exponential of a small number. So a small number, it is close to 0. So we have 255 divided by 1 plus something that is close to 0. So it has to go to 255. So we go to there. What happens at 127? So at 127, this is 0. This argument is 0. The exponential of 0, what is it? What is it? 1. And then we have 255 divided by 2. So we have 127. So it is a function that goes through these 3 points. And what is it doing in between? Okay, this is a bit more complicated. But if you plot it, if you take these, make these calculations carefully, you will see that it goes something like that. And actually, the slope of this transition depends on A. Okay, so we can have functions like this that goes more quickly. We can have functions that go more smoothly. Okay, so let's try to give. So we have A1, the blue one. We have A2. That is the red one, and we have A3, which is the A corresponding to the green one. So what are the relationships between the two? So you would expect A1 to be larger or smaller A2? So smaller. The same here. Okay. So the smaller the A, the smoother the transition from 0 to 255. Actually, if A is too small, it doesn't need to go strictly to 0. Okay? It may start, so let's say that we have an A that is too small, A0 for instance, it may start here and go very smoothly up to here, and it doesn't need to go to 255. So it depends on what is A0. Okay, good. Yeah, actually, what happens if A is equal to 0, for instance? It's flat. We have flat transformation. Is it invertible? flat transformation is invertible. If I tell you the output is 127, it is not. I don't know what is the input value, so it is not invertible. Okay, good. And it looks like this. Yeah, this is MATLAB code to compute that. Okay, yeah, this is the same idea. We can have different functions for different bands. Yeah, same idea again. So if you have a color image like this one, you would have 3 lookup tables or 1 lookup table. So what you do is, for every pixel in the 3 channels, you go to the lookup table and substitute the input value 64, for instance, by 32. That is what you put in your output. And you do that for the three bands. Okay, then this is an example of this 3-band separation, and then we will apply different functions to each one of the channels. Okay, so let's, we separate, and now we will apply this function to each one, or these functions to each one of the channels. So the red channel we will apply this sigmoid function. To the green channel we will apply this inverted function. And for the blue channel, part of it will be simply scaling, so we are simply multiplying by 2. But for the other half, we are multiplying by 2 and inverting, so this is an inverted part. Okay, so let's see if it makes sense what we see. So for instance, here, let's see the red channel. So what is the red channel? So the red channel has this bright standard there, and then we have a very dark background. Okay, so what happens? The dark background becomes even darker because of these. So you see that all these dark values, they are even more down in the output. And the standard becomes saturated because all this area, all these values, they take almost the same value. Okay, so let's compare the red channel. So what happens? So the red channel is saturated on the bright values and on the dark values. You see? Okay, so let's look at the green channel. So the green channel is now whatever was dark, because we are inverting, now will be bright, and whatever was bright now will be dark. Okay, this is what's happening. So whatever was dark now is bright, whatever was bright now is dark. Okay, and the blue channel. Okay, the blue channel is halfway. So up to the middle, values should be brighter. From the middle to the end, values should be inverted. That is what's happening. Okay? So all the background that was relatively dark, let's look at it here. All the background that was relatively dark now is brighter. And all the values that were relatively bright, now they are inverted and now they should be dark. So you can be very creative about what is the transformation. By the way, this transformation is invertible. Forgetting about the rounding and the saturation. Okay. So let's say that this saturation doesn't exist. It's invertible. Can I recover the original image from this one? Why not?
Due to saturation. We will miss information.
Which one?
When we put the 3 of them together,
Yeah.
due to saturation at some point, we will
No,
miss
forgetting
information.
about the saturation.
In the only channel that we can recover the original values, the green one.
Say it again.
The only channel in which we can recover the original value is the green one. Because it's the only one that has only one
Yeah, the green is
One-to-one.
clearly invertible. It is 1-to-1. The red, except for the saturation, it is invertible.
Yeah.
But the blue one is not invertible. I tell you that the blue was, the output blue is 150. You don't know which one of these two values are. Okay, so the blue is clearly not invertible. Now you have a beautiful transformation. So the information is almost the same. It is almost the same because of this non-invertibility of the blue channel and the saturation. But the saturation is something, if you have enough precision, if you have enough bits, all these values, they are not exactly the same. Okay. So yeah, so now let's go for these transformations. Okay, so let's say that we have that image there, and this is the luminance histogram, and now we understand what is the luminance. Then we will construct the following transformation. So the output image will be the input plus D. So we are shifting all the gray values up by a given amount D that is positive, and we apply the same transformation for the all values. We have a problem that is, okay, so this is the identity transformation. So now you give me any input value, I will produce the identity plus some extra shift G. But then, from this point, if I take 255 plus G, it's larger than 255, so I cannot represent it with 8 bits. So I have to click 255, and it will happen for all these G previous values. So if the shift is G, this is also G. Okay? So all these values I have to click at 255. And then all those points will become saturated. And we see the saturation here. We see this spike as if the histogram has been cut. And let's compare to the original histogram. So we shift all the values to the right, and then all this band becomes is cut and collapses at a single value 255. Okay? But otherwise, the image should look brighter because we are shifting all the values up, and it does. Okay, so this is the original, this is the shifted up. Okay, and the shifting down. So shifting down is the same, but now we are subtracting a value rather than adding a value. Okay, so these two operations are called increasing brightness and decreasing brightness. So no wonder. Okay, good. Then we can decrease the contrast. Okay, so decreasing the contrast is the following. So we take the input value, we center it at some point, so this point, central point S, then multiply by A is a number that is between 0 and 1, and then we add S again. Okay, so let's look at this a bit more carefully. Okay, so now, you know about coordinate changes. Okay, so let me use the colors for not for the input output, but for the coordinate axis. Okay, so let's say that this identity, the identity transformation, so I prime equals I, and my origin is here. So this is the 0, 0 point. But I may shift the origin to some other point. I may shift the origin to here. And then I have a center I, a center I prime. And this will be the 0, 0 in the new coordinate system. How do I do that transformation? So I tilde is I minus some s. Okay, so let's shift it at s. And I prime tilde is I prime s. So I have a new coordinate system. In this new coordinate system that I have named with tilde, the relationship between these two images, input output, it is the one this one. So it is a very simple transformation. So it is a line of a slope that is smaller than 1, because A is between 0 and 1. And now I have to undo the coordinate transformation. So if I undo the coordinate transformation, let's make it black again. So then this will be I prime minus x. It's A prime minus x. And then we can solve for I prime. So this trick of minus s plus s is simply a shift of the coordinate system. So for the moment, we have shifted the coordinate system to some other location, particular to the location. Let's make it right. This point here is the s coordinate, and then this trick of subtracting and adding is simply a shift of the coordinate system. Any question? By the way, I have given you in this Teams channel, I have given you a couple of books that I normally edit on biomedical engineering, so on research of biomedical engineering. So I ask teachers or professors from other universities to tell what they are working on in terms of research. And here are the two books, this one here, and this one, 14 and 18. And the books are free, so you simply click on them and you get the book. And you can even buy them if you want them in paper, but probably you don't want. Okay, and you see what are the different people working on at different universities. This is just, biomedical engineering is somehow very much linked to research. So it's a discipline in which research is very active. So I don't mean in other engineering disciplines, it is not, but it is really, really active in biomedical engineering. So learning what people are doing is really useful, because probably you will work in any one of these applications. Okay, let's go back to our slides. Okay, so now we understand the transformation. So the transformation is exactly what we described on the whiteboard. So we have, this is the input, this is the output, then we have shifted the coordinate axis to this point, SS, and here in this example, S is 127, and then in that coordinate axis, the blue one, the transformation has a slope that is smaller than 1. Okay, so identity has 1 slope, so a slope equal 1. If you are below identity, so you have a slope smaller than 1. If you are above the identity, you have a slope larger than 1. And we understand why now it is called a decrease of contrast. So we define contrast in a kind of loose way as the difference between minimum and maximum. So let's say that our input image goes from 0 to 255. So that is the contrast, 255 minus 0. After the transformation, the output, we have a maximum value that is smaller than 255, and we have a minimum value that is larger than 0. So this difference will be smaller than the input. And this smaller difference is that the difference is also called the dynamic range. So the dynamic range in the input goes from 0 to 255. Here it goes, I don't know, from 60 something to hundreds. Okay, so the dynamic range here is smaller than in the input. And that is what we see. So we see less contrast in our input image. So we can compare the original. So the original was this one. And now, and look at the histogram also. So the histogram goes from around 40 to 250. And now, sorry, it goes from, it is much more concentrated at the 127 value. And we don't see so much difference between the minimum and maximum. So everything becomes more or less all the same. Actually, if A is equal 0, it would be completely flat. So again, if A is 0, we would have the flat transformation and everything would become the same color. Okay, good. Then we can increase the contrast. So it is the same transformation, but now A, instead of being smaller than between 0 and 1, now A is larger than 1. Now the slope here, the slope is more than identity, and we are increasing the contrast. If we are keeping our images in 8 bits, then we have to saturate, because all these points here, they will have an output that is larger than 255, and all these points here, they will have an output that is smaller than 0. We cannot represent those values in our 8-bit representation with unsigned integers. So we have to saturate, and then we saturate the negative numbers, and we saturate the numbers larger than 255. And we see the saturation again here in the histogram. We also see the saturation in the image. So for instance, this area here is saturated, this area here is saturated, and then probably these parts in the forest are also saturated. And we may compare, so we are increasing the contrast, and we compare to the input. Yeah, so this is the input, and yeah, we have increased certainly the contrast. We have to pay some price, and the price is the saturation of the very high values and the very low values. But things are more contrasted. We can see better the differences between maximum and minimum. So for instance, another region that is saturated is this one here in the windows. There were a lot of details in the windows, and these details are lost due to the saturation. Okay, then we can stretch the contrast. So this transformation we already know, we introduced it the other day. So if you have an input image that is whose minimum and maximum are this small m, capital M, you may scale them to have any arbitrary output minimum and maximum. So you define what are the minimum and maximum that you want in the output image, and typically those are 0 to 55. And then you scale your input image with this transformation to get the output. And is this a linear transformation? Is it linear in I? What is the shape of that transformation mathematically? So it looks complicated, but it has this shape at the end. So it has, he's using J instead of I prime. For me, this is I prime. So this has this form, AI plus D. Only that this D and A, they look complicated, but they are simply constants. Okay, so those are straight lines. You see that it has that structure. So J depends linearly on I, and then all the rest they are simply constants. So it has this shape of a first order polynomial. And and then what we are doing is transforming this line, instead of having a slope 1 or a slope A, we define the slope through these minimum and maximum values. Okay, then have we lost information? Okay, let's see. Okay, so let's say that I have an original image, and then this is the histogram. And this, let's say that it has a contrast 1. So contrast 1 meaning it has a reference contrast. So now we decrease the contrast. Okay, so we decrease the contrast, and we know which transformation we use for that. So we use this one with A equal 1/2. So we decrease the contrast by a factor of 1/2, and we know that everything is concentrated towards the central point, so this 127. And now this image will restore the contrast. Okay, so now, we multiply by 1/2, and now we multiply by 2. Okay, so let's see what happens. And this is the histogram of the one that follows these two operations in a row. So first decreasing the contrast and then multiplying the contrast. So, or increasing the contrast. So this is dividing by 1/2. This is multiplying by 2. So we get the same thing. The reason is this rounding. Okay, so let's go to our, so let's try to understand that process. So we have an input image. Let's say that we have an input image I. We are producing I prime, that is 1/2 of I, and we have to shift this 127 plus 127. So the colors actually they have to do with in which axis you are shifting your coordinate system. Okay, and then we construct a new one. So this I second will be twice, and then the input to this one will be 100 minus 127 plus 127. So if we want to represent this process, we would have first an image I that goes into something that multiplies by 1/2, and then we have I prime, and then we enter into something that multiplies by 2, and then we get I second. Okay, so these two systems, they seem to be the opposite of each other, so the inverse of each other. So why do we lose information? And the reason is this quantization. Okay, so let's see. So we start, let's say, with the value 127. So we subtract 127, so we get 0, divide by 2, but we get 0 again, and then this will be 127. And then we multiply by 2. So subtract 127, so we have 0, multiply by 2, so we have 0 again, and we have 127. Okay, so this point doesn't move, and this is expected. Okay, so what happens with 128? Okay, you substitute it here, and then you get 1 divided by 2. Let's say that the rounding is always down. So we get 0 again, and then we get here 127. And 127, we have another division that marks to 127. So, and what about 129? 129, we get 2 divided by 2, 1, so we get here 128. And this 128 will give us here 129. This is step 2, and the same will happen. So we don't follow now the whole track. 130 will map onto 129, and then 131 will map onto 131. So you see that it goes in steps of 2. So these two values, they map to the same value. And these two values, they map onto the same value. And we go in steps of 2. This delta here is steps of 2. So there is no way that we can get a 128 there. Okay? So that is what we are seeing in these histograms. So in these histograms, we see holes. The holes are coming from the values that cannot be reached. And actually, if you look at this one, the maximum height, let's say it is around 1500s. But now, the maximum height here is around 3000. So why? Because with 1500s, we are adding the values from 127 and 128, and we are collapsing them to 127. So a bar here is collecting information from 2 bars from the original image. Okay, so quantization is okay, that it is not a terrible thing, but it is not such a good operation. You see? So many of these operations, when you have to work in reality, they are done with real numbers. So when you want really to manipulate your images in doing mathematical transformations, instead of using unsigned integers, you use real numbers. And the same happens with, if you take the original, now you multiply by 2, and then you reduce by half. So it is the opposite. Okay? So instead of this path here, what we have is the opposite. So we would have I goes into a system, and then, this system is multiplied by 2, we have I prime, and then we enter into another system that is divided by 2. Okay, so now, because we are multiplied by 2, we will have to saturate, and we will have these holes in between. So now we understand where the holes are coming in. So we are multiplying by 2. So we are going in steps of 2 in the output. And then when we reduce the contrast again, so the saturated values will stay. And now we don't have any longer these steps of 2 because we are divided by 2, and then all the values are accessible, all the output values are accessible. So if you multiply by 2, you have holes. If you divide by 2, you don't have holes. Okay. Any question here? No. Okay, good. Then we can compute what are the differences between the original image and all these contrast changes that we have done. Okay, so this is the one that reduced the contrast. This is the one that increased the contrast. So this is divided by 2, multiplied by 2. And then we take this one, restore the contrast. So divide by 2, multiply by 2. So in principle, we should get something similar to the original. And actually, if you compute the difference looks like noise. There is only a region where you see systematic problems that are this one. So in that area, you have something that is not noise. Okay? But otherwise, it is simply just these small differences between the original values that we have. So we have here the transformations. So we had 130, and this 130 was transformed into 129. So there is a difference of +1 or -1. So these small differences are the ones that we are seeing in these different images. What about the other one? We were multiplying by 2, so we were increasing the contrast, multiplying by 2, and then dividing by 2. And again, it looks more or less like this one, but the areas that were saturated, that information is lost. Okay? So all this information here is lost, all this information here is lost. And then when you compute the difference with respect to the original, it is not just noise. So you have significantly lost information from your image. Okay, so here we have lost the information. It is not anything terrible. Here we have lost a lot of information. So invertibility is not only the single criteria. This transformation is not invertible. So this one here is not invertible, but it doesn't lose much. This transformation going multiplied by 2, saturating, and then restoring, is not invertible either, but you have lost a lot. So invertibility is not the single criteria. Okay, good. Any question? Okay, let's go for gamma. So gamma is refers to this transformation there, and this transformation actually we understand what it is doing. So it is taking the image. The image is between 0 and 255. So now we are divided by 255. So now this ratio is between 0 and 1. Then we are taking that value to the power 1 over gamma, with gamma larger than 0. And so if this is between 0 and 1, this is kind of the gamma root of this number. So the gamma root of this number will also be between 0 and 1. And then we scale it back to 0 to 55. It is kind of the same trick that we did before by shifting the coordinate axis, but now we are compressing and expanding the coordinate axis. And actually, let's do that. It is an interesting exercise. Okay, so let's move it here. So we have an image. Goes like this. So it is I prime goes to 255, and then I divided by 255 1 over gamma. Okay, so let's manipulate this a bit. So we will have I prime divided by 255, and this is equal to I divided by 255 1 over gamma. And now I can define my new axis, my new variables. I tilde prime, that is equal to this, is equal to I prime, I tilde, sorry, square gamma root of that. So this is my main relationship. This is my main relationship between the two variables. And then the tildes reflect the fact that the images have been rescaled. So let's make plot for these. So, so here we have I prime. They go from 0 to 255, and here so. And if we make the plot in the I tilde space, they go from 0 to 1. So the transformation is the same, but now I have rescaled my axis so that here it looks like this. So this is this. Let me plot it. I tilde prime is I tilde 1 over gamma. So it is the gamma root of I tilde. And the shape of this is exactly the same here, only that the axes have changed. Okay, so this idea of compressing and decompressing is equivalent. So this idea of compressing and decompressing is equivalent to this idea here that we had of shifting and then shifting back to the original location. Okay, good. Then here we have the gamma transformation for gamma larger than 1. So one question. This transformation is increasing or decreasing the contrast? It's doing both at the same time. So we said that the contrast is decreased if the slope is smaller than 1, and increased if the slope is larger than 1. So here, the slope is larger than 1. Here, the slope is smaller than 1. So for the dark values, we are increasing the contrast. For the bright values, we are decreasing the contrast. So yeah, this is the result. So the dark values, the dark areas, we are increasing the contrast. This area was rather dark. We are increasing the contrast. This area that is bright, we are increasing the contrast, and we see a bit less details. And if gamma is smaller than 1, then we have the opposite. So the dark values, we are decreasing the contrast, and for the bright values, we are increasing the contrast. So now this area is much better seen, and we are losing the details in the dark areas. This transformation, aside from the quantization, this transformation is invertible. If I tell you the output, can you compute the input? It is. So for every value, the output, that's a single input value. So aside from the quantization effects, it is invertible. Okay, so what happens if we play the same game as before? So we apply gamma transformation and then the opposite gamma transformation. In principle, we should get the original image. Okay, so let's see that. Okay, so let's start with gamma equal 2. So we are increasing the contrast. So it is the one that looks like a square root. This is a square root actually. So we are increasing the contrast in the dark areas and reducing in the bright. Okay, so we are creating holes in the dark areas, and we know now these spikes where they're coming from. So they're coming from the addition two values, two input gray values that collapse onto the same output value as we had before. And this is with gamma equal 1/2. So with gamma equal 1/2, now we are creating holes in the bright areas. So there are some bright areas, some bright gray values that cannot be reached by transformation. And some of the dark colors, they are collapsed onto the same value. And then we have these spikes. Good. Okay, this is a reminder of what the PDF is. Remind all these. Okay, so let's look at the PDF and CDF of all these things. Okay, so yeah, this is the PDF. The PDF, just a reminder, the area has to be 1, and the CDF, here it is using capital PDF, but I think it is better to use CDF. So the CDF is just the integral up to that point. So for instance here, up to 150, what is all this sum of values? So it is like 80 or 85. So let's say 85% of the input pixels, they have a value that is smaller than 150. Okay, good. Okay, so what if I use the CDF to construct the lookup table. Okay, so let's do that. Okay, so I have the lookup table. Forget about the plus ones. This is something of math. So I take the lookup table, multiply by 255. So let's see what we are doing. Okay, so we have an image I, then we have the CDF of I, and then we have here 255 times the CDF. Okay, so yeah, this goes like 0, 1, 2, 255, and this goes, I don't know, what are the number of values that are smaller or equal, let's put the definition, is the probability that a single pixel of I is smaller or equal that value. Okay, so this is D. This is D. Okay, so it is smaller or equal 0, smaller or equal 1, smaller or equal 2. So let's say that 5% of the pixels are smaller or equal 0. Then 6% of the pixels are smaller or equal 1, and so on. How many pixels are smaller or equal to 55? All of them. Okay. Now I multiply this by 255 and quantize it. So 255 multiplied by 5, I don't know, is 10, let's say. So this would be 10. You do the multiplication yourself, okay? And this is 11. And it goes all the way to 255. But now if I look at this, I have a lookup table. So what if I use this function as my lookup table? That is called histogram equalization. So this is called histogram equalization. Okay, so let's see the effect. Okay, so this is our lookup table. And now I can even, for instance, I can actually see that here I'm mapping 0 to 10. Okay, why don't I apply another transformation now, a blue one. Now I apply a blue one. And let's make it more specific. This is our red image. Okay, so this is our prime. And I can construct a second. That is the scaling of I prime. Now this scaling, we know what it is. It is simply scaling it between 0 and 255. So I look, okay, what are these two input and output values? What is the minimum and maximum that you are producing with this transformation? And I can scale them to 0 to 55. Okay, so this is the other transformation. This other transformation is doing that. So the first part, all this part, is doing I prime, and then this second part is doing this, the I second. Okay, good. Okay, so if this is my value image with this PDF, this is the CDF, and this is the result of this histogram equalization operation. There is a property now that is all the output values, regions, they have almost the same probability. And we will reason about that later. Okay, so this is just the description of the process. So first you compute the CDF that goes from 0 to 1, and then you scale it to a lookup table. When you realize, okay, all these values, they have 0 outputs. So I don't have any input value between 0 and 40. So the lookup table, all these values will be mapped to 0, and then my output image will have zeros there, and that is why I'm using the scaling operator to map them back to 0 to 55. Okay. And in this drawing, we see is it increasing or decreasing the contrast? Well, it depends. It depends on the slope. So in those areas where the slope is larger than 1, we are increasing the contrast. In those areas where the slope is smaller than 1, we are decreasing the contrast. Okay, so if we take regular values here, if we take regular values there, it turns out that all these values here, they are mapped almost to the same range. They are not exactly the same number, but there is a very small range there. Okay, why? Because there were few bright values. If you have few bright values, why spending so much gray values onto pixels that will be seldom used? So better collapse all those values to some small region. And the area where you have a lot of pixels, you expand the contrast there. And then all this area of dark, relatively dark values will be using the whole dynamic range. So you give more dynamic range to the areas where you have more pixels, and less dynamic range in the areas where you have fewer pixels. So I don't think that we have the opposite picture. Okay, but it is related to this. So now, what is the probability that if we take any value in the output, so let's go here. Okay, so now we have this transformation. This is I, this is I prime, this is prime, this transformation there. So now instead of taking regular intervals in I take regular intervals in I prime. So I divide I prime in 5 pieces. Let's look at instead of the lookup table, let's look at the CDF. So this will be the CDF. This will be the CDF of I prime. So forget about this one. So if I put I prime, it is a lookup table. If I put this thing, it is the CDF. Okay, so what is this? I have divided the output in 5 pieces. So from 0 to 0.2, 0.4, 0.6, 0.8, and 1. Okay, so what is the probability of having an output value in this area? It's 0.2. And here, 0.2. Okay. So all the steps have 0.2. So that means that the probability of having a value at regular intervals in the output image is all the time the same. That is why this operation is called histogram equalization. If you take regular intervals in the output, we have all the same probability. Approximately. Okay, good. So let's see the CDFs and the histograms of this transformation. So this is the histogram of the input image, and this is the histogram of the output. And now we recognize this process of creating holes in the areas where we are increasing the contrast, and then having spikes in those areas where we are decreasing the contrast. They collapse to the same value. And we see the scaling. So you see that this 40 has been mapped to 0. So we see here I prime and I second. Okay, so I prime is the histogram equalization, I second is scaling it back to 0 to 55. Yeah, so this is the luminance image, the luminance histogram, the luminance CDF, and this is the equalization lookup table. So there's single difference between this plot and the following one. This goes from 0 to 1, the other one goes from 0 to 255, and then we apply that equalization to the luminance image, and that is what we get. Any questions? Okay, yeah, so the comparison of the two. Okay, so now, what if I do the following? So I have the original image, I have the corresponding bands and the histogram of those bands, and I do this correction, this histogram equalization for each one of the bands independently. So each band will have its own CDF, and then its own lookup table, and then when I apply it, this is what I get. Okay, so we know we haven't lost information because that transformation is invertible, but yeah, except for the quantization effects. But it looks weird. Okay, so what if I do the following? So yeah, that's some kind of unnatural colors in the equalized image. What if I do the following? I start again, and then I used the CDF of the luminance. So before, in my previous transformation, I was using the CDF of each one of the color bands. But now I use the CDF of the luminance. So I use the CDF of the luminance, 3 bands. Okay, so then I get this one. And yeah, so the colors, okay, they are not the same as in the input, but that is why we have used this transformation. We wanted to have better contrast in those areas where we had more pixels. But they look more natural. You can compare this image here to the one that we had before, that was this one. These colors were really, really unnatural. The relationship between colors, they were not respected. It was not respected. But here, by using the luminance, okay, again, they look a bit artificial, but much less artificial than before. So the relative relationship between colors, now it has been respected. Any question here? No? Okay. Fine. Okay, so next we will see this other operation. This is called histogram matching. And let me show you the result before. So why we want to do this, and then we will go to the details. So the histogram matching is here. This is what I want. Okay, so let's say that you have 2 pictures of the same area, but they are 2 different pictures. So you see, it is the same garden, but somehow your camera here was working correctly. These are the camera, the color sensors, they were not so accurate. So you see that these colors are artificially, they do not look like the ones in nature. Okay, so can I correct this one to look like this one? So what I can do is to compute the histogram of this image and somehow transform this image so that the histogram of the 2, they are similar to each other. And then, after applying that, I will get this one, which is much more natural colors. You see? And the same can happen, for instance, with you have 2 cameras pointing to the same area. One of the cameras is working like that, the other one is a bit saturated. And then after matching the histogram, you get both with the same kind of curves. Okay, so let's see how to do this for histogram matching. So let's go to the. Okay, so let's go to here. So you have two images, I and J, and you have the histogram of I, you have the histogram of J, and you want the two histograms to be relatively similar. You will never get them to be exactly the same. It's the same with the histogram equalization. You can never, so histogram equalization tends to make the histogram flat, but it never completely achieves flatness. Okay, so we have the two images, we have the two histograms, and then I have to construct this lookup table. And let's see an example of how we can do that. Okay, so I have to look for every input value, what is the corresponding output value. And the corresponding will be the following. Okay, so let's consider 5, value 5. What is the corresponding in the second image for value 5? Okay, so if I look in my image I see that 65% of the pixels, they have a value that is smaller or equal to 5. Then I look for an equivalent point in the image J. So I have to look for a value such that 65% of the pixels are smaller or equal to 5, or that value. So that value is 10. So that value is 10. Isn't exactly not 65%, it's a little bit higher. But if I take the previous value, it is too low. If I take the next value, it is too high. So this 10 is the closest one. I have to formalize that. So this is the formalization. Okay, so the corresponding GI goes to GJ if the CDF at GI is larger than the CDF at GJ minus 1, and the CDF of GI is smaller or equal than the CDF of GJ. Okay. So I have to formalize that and give a precise rules. But the idea is clear. So I have to find a value. If this is 65%, I have to look for a value here that approximately 65% of the values are below that point. So then my lookup table will map 5, 10. Okay, this is the pseudo MATLAB code to do that. And let's see some examples. So let's say we work with few colors so that we can track the PDFs and so on. So let's have this image with only 16 values. So that is the histogram, and then this is the CDF, and then we have another image. This is the PDF of that image, the CDF of that image, and I want to transfer. This is MATLAB code again. I have to transfer the CDF of one onto the CDF of the other, and that will give me the lookup table. And again, let's look for the processing. So this 4 value, 60% of the values of the first image have a value that is smaller or equal to 4. And then I have to look for a corresponding value in the second image, such that approximately the same amount of pixels have a value that is smaller or equal to that value. That will map 4 into 10. And then you can map all these, you can check all the mapping. So for instance here, all these values are saturated, almost saturated. So all these outcomes will be saturated at 15, so they will have the same output value. And the precise, so I'm a little bit loose by saying approximately the same. The precise definition is this one. Precise definition is this one. So the mapping is such that this rule is fulfilled. Okay, then we do the mapping, Again, this is MATLAB tool for that. So this is the input. This is the CDF of the input. This is the CDF of the target. This is our lookup table. And this is our result. So as I said before, it is not exactly the target. So we are trying to modify the input such that it looks like the target, but we cannot make it exactly look like the target. It is more similar to the target, but not exactly the same. And again, with these images, these effects are exaggerated because we have very few gray values. But if you have more bits, it's more like a continuous. Okay, so that is the original, that is the target, and this is the remapped one. So we are remapping this image such that the histogram looks like this one. And it is true, those are two different images, but the histogram will look more or less the same. They have the same kind of contrast, more or less the same kind of gray values, brightness, and so on. And by doing this transformation, we can adapt these images of the flowers and the boxes. Okay, this is another example. We have that color image. We have the different PDFs, the different CDFs, and then another. We apply. This is a different image with the different PDFs and CDFs, and then we remap this one to have the same kind of histogram as this one. Okay, they're not the same, so they're two different images, but somehow they have the same luminosity. Here the remapping has been done on luminosity, and it is true that they have more or less the same. And here is the whole process fully detailed. So we have the CDF of the luminosity of the first one, the CDF of the luminosity of the second one, the lookup table, and the remap. Different histograms. We understand now these folds, these spikes. Okay? So a spike is decreasing contrast, creating holes is increasing contrast. Yeah. And all these are small details about these transformations. Okay, so now we can use so we had this histogram equalization in which each one of the lookup table of each one of the bands was the CDF of the luminosity. And here we are applying this lookup table. So this lookup table is the CDF of the band, and then composed by the inverse of the CDF of the luminosity.